A totally relevant question is, how can we benefit from the computational speedup through fast convolution in frame-based processing? There are two different ways of implementing fast convolution in a frame-based fashion. Firstly, overlap-add fast convolution, in which all values of the result that are located beyond the frame are added to the future frame. Secondly, overlap-safe fast convolution, in which we use only those values of the result that are not corrupted by time aliasing. I'm going to demonstrate both approaches in the following. Let's start with overlap-add fast convolution. At the top, you see the input signal divided in frames of equal duration. At the bottom, you see the placeholders for the corresponding frames of the output signal. So the first frame of our output signal arrives. We zero pad it according to the length of the impulse response that we want to convolve with. This is indicated by the dark shading. Here, the impulse response is rather short, but it may actually be of any length. It can even be longer than a signal frame. We perform the fast convolution and note that its result is longer than the output signal frame we want to compute. So there will be a slight overhang when we add this temporary result to the output buffer. Now we go ahead and process the second frame of the input signal. We zero pad and perform the fast convolution with our impulse response. When adding the result to the output buffer, it will overlap with the overhang of the previous processing frame, and we have to add the two. It will now be obvious why the method is called overlap add, because we add the output wherever it overlaps. We go ahead in a similar fashion until the end of our input signal, until the entire input signal has been processed. The alternative to overlap add fast convolution is called overlap safe. It is based on the observation that when zero padding the impulse response by a given number of zeros, then the result of the fast convolution will contain at least the same number of samples that are free from time aliasing. This is illustrated here. At the top, there is our signal, and the middle plot depicts the impulse response we want to convolve with in blue. It happens to be half as long as the signal, so we zero pad it appropriately so that it has equal length. This is indicated in red. If we now perform the fast convolution, then the green samples of the output signal are guaranteed to be free of aliasing. The blue samples of the output signal are not guaranteed to be free of it. You can even see a bit of time aliasing here. There are, of course, different choices for the amount of zeros that the impulse response is padded with. I will show you in a particular choice that is the one that I favor personally, because its implementation is particularly convenient. So here we go. Our input signal cut into frames is again indicated at the top, and the corresponding frames of the output signal are indicated at the bottom. For overlap safe, it's more elegant not to process one frame of the input signal at a time, but two of it, like this. We zero pad our impulse response by one entire frame. Note that there is a constraint with respect to the length of the impulse response here. It must not be longer than one signal frame. If it's shorter, then you just zero pad a little more. From the considerations that are presented to you on the previous slide, we know that the first half of the result of the fast convolution is potentially be corrupted by time aliasing. So we cannot trust it, and we toss it. This then yields the output frame that corresponds to the second frame of the input signal. We then move on and process frames 2 and 3 of the input signal to yield frame 3 of the output signal, and so forth. So the overlap takes place on the input signal side, and we save the uncorrupted samples at the output. This is why it is called overlap safe fast convolution. Now, you might ask yourself how to obtain the very first sample, the very first frame of the output signal. Well, that's very simple. Just prepend one frame of zeros to the input signal, like this, before starting the processing. When dealing with impulse responses that are longer than a signal frame, it might be beneficial or even required for some implementation strategies to partition the impulse response. One then speaks of a partitioned or of a segmented convolution. Assume the impulse response of length 16 depicted in the top plot, and assume that the frame size of the system we're using is 8. So the impulse response is 2 frames long. We can represent our impulse response h of t as a sum of 2 impulse responses, h1 of t and h2, that exhibit non-zero taps only in the first half or only in the second half, respectively, as indicated by the middle and the bottom plot. We note that convolution is distributive, meaning that the convolution with a sum of signals is identical to summing the convolutions with the individual signals. This tail of zeros of h1 has absolutely no effect on the result of the convolution, so we can simply ignore it. The effect of the leading zeros of h2 will be a delay of precisely 1 signal frame. So we can ignore these zeros too if we make sure that their effect is taken into account when calculating the result of a convolution with h2. So we have cut our initial impulse response into 2 impulse responses of half the length each, plus a bit of meta information on the inherent delays. How can we make use of this in a frame-based signal processing system? Assume that the impulse response h indicated at the top has a length of precisely 3 signal frames, and that we cut it in 3 impulse responses, h1, h2, and h3, that each are precisely 1 signal frame long. By the way, if it were a little shorter than a multiple of the frame size, then we would, of course, zero pad it a bit. When processing the first frame of the input signal, we only need to convolve it with h1, as h2 and h3 have no effect on the result at this point. We can use time domain convolution for it, or overlap add, or overlap save, whichever you prefer. So we got our first output frame. When processing the second frame of the input signal, we convolve it with h1, but we also need to take h2 into account and the leading delay that we removed from it. This is why we convolve x1 with h2 here, 2. And add up the results to yield the output buffer. We continue like this, and not forgetting the third partition, h3, which we convolve with x1, and so forth. With this method, you can process impulse responses of arbitrary length, no matter what the frame size of the underlying signal processing system happens to be. So far, we've always assumed that the impulse response we're convolving with does not change. In many practical applications, we want to replace the impulse response dynamically. There's actually a comprehensive theory for such time-variant systems. However, for our purposes, this is total overkill. Practitioners, they follow a much simpler route, which is the following. Our input signal frames are again depicted at the top, and the output signal frames are depicted at the bottom. When you want to replace the impulse response hm-1 with another impulse response hm, we convolve the current signal frame x of m with both the previous impulse response h index m-1 as well as separately with the updated impulse response hm. We then fade out the result of the convolution with h index m-1 and fade in the result of the convolution with h index m. The fades are indicated by these blue curves. So we can do this with every frame of the input signal, convolve with the previous and the current impulse response and crossfade between them. If the previous and the current impulse responses are not too different, then the transition will sound very smooth. There are, however, things that can go wrong in the crossfades. Assume that we want to crossfade between the blue and the green signals that are 2 sine waves of identical amplitude and frequency that are shifted by half a period relative to each other. The fade takes place between the vertical dotted lines, and the cosine-shaped fade slopes are indicated by the black solid lines. The result of the fade is shown in orange in the bottom plot. As a result of the crossfade, the instantaneous frequency of the output can be totally different than the instantaneous frequencies of the input signal. This can result in clearly audible artifacts. And many times there's simply nothing that you can do about it. You can fiddle around with crossfade durations and such, but the possibilities are limited. Fortunately, in real life, it is rare that we want to crossfade between sine waves. We're usually dealing with significantly more complex signals, and that makes things a lot easier. For example, crossfading between two noise signals like these ones will be totally smooth. But if you happen to hear unexpected artifacts in the output of a dynamic convolution, you now know what to double check.